thank you all so much for joining us on your busy Fridays, I think. I don't really know what day of the week it is anymore. Us here at Team Explorer are absolutely thrilled to tell you a little bit about the latest, greatest interdisciplinary, intercontinental, interplanetary mission to a little moon called Titan that every space agency is talking about. So it's called the Oracle. First, some thanks to our sponsors. There are many, and they're fantastic for enabling this to happen. This has been an amazing experience.
So where do we start? This is a really interesting question, and NASA gives us a bit of a guideline in the form of the decadal survey, which is released every 10 years. And so the most recent one, which we have to go off of, had 3 key questions that they wanted to highlight within planetary science. The first topic was building new worlds. So how are solar systems begun? Where do they start? What are the processes guiding this? The second one is planetary habitat. This ties in deeply to astrobiology. Are we the only planet to have life on it? Is there life elsewhere? What are the requirements? Where can we find biosignatures? And finally, what are the workings of the solar system? What are the dynamics, the planetary processes, and how do they change and modulate throughout time? So when we combine all these together, and we look in the solar system for a target, ta-da, Titan, my favorite. So Titan is a great place to go for these specific targets because it's a really dynamic world. So this is an image from the Huygens descent, showing kind of some of the mountain features in the mid-latitudes where Huygens descended. But Titan actually has kind of some differentiation in its layers. So it's got the rocky core, and it has this subsurface water ocean. It's got an icy crust, and then a veneer of organics on top, and a really thick atmosphere, which really differentiates it from other moons in the solar system. And on the left, we have a geomorphological spatial map, which indicates some of the different surface features that we see on Titan. It's really very spatially and latitudinally differentiated. So we see in the middle, we have these dunes. The plains kind of reach the mid-latitudes, both north and south. And then at the poles, we have the lakes, which is kind of the focus of our mission today. So we've been to Titan before. We have several missions. One was the Cassini and Huygens orbiter and landers, relatively. And they, from 2004 to 2017, Cassini conducted 126 flybys of Titan, taking really invaluable mapping, spectroscopy, and imaging data. Dragonfly hasn't landed yet, but in 2034, it's this little quadcopter, which will land around the equatorial regions and jump around, doing a lot of prebiotic analysis and study. So why should we go back? Because we haven't been to the lake regions yet. So remember, the lakes are up at the poles, and the lakes are one of the highest value landing spots in the entire solar system for studying some of these key planetary science questions. So the lake regions really are the union of some of the most critical and unique processes on Titan. The first being atmospheric organic photochemistry. So when the sunlight hits the organics in the atmosphere, it causes the normally non-reactive nitrogen and methane to break apart and ionize. These recombine and form much more reactive and slightly more interesting chemical species, which then eventually, as they become heavier and heavier, drift down onto the surface and potentially even go down through the surface to this liquid water ocean, where if there's life as we know it on Earth, we would expect it to be down here. The second really interesting process that's happening around the Titan lakes is the hydrology. So besides Earth, Titan is the only place with a hydrologic cycle in our solar system. So here we have a water hydrological system, but their cycle is actually hydrocarbons, so methane and ethane, due to the really cold surface temperature of Titan. So we have these hydrocarbon lake systems at the poles. It rains methane and ethane, and we have these cloud systems. And this hydrologic cycle really differentiates Titan from basically any other moon in our solar system. And the final one is geology. So Titan's surface is really pretty young compared to most satellite surfaces. It's very dynamic, and there's a lot of processes, both fluvial and pluvial, as well as just different tectonic activity. There's putative cryovolcanism there. And so all of these different interactions combined with the hydrology and the photochemistry make this a really key landing site. So we have got to go back to Titan because we have got to study these lake systems. So our science goals are twofold. The first is to profile Titan Sea and to really understand this interaction of these 3 key features of Titan. So we want to conduct a thorough characterization of Ligeia Mare, which is the second biggest body of surface liquid on Titan. So it's up at the North Pole. This is an image from the Cassini radar image here on the right. And so we specifically have a suite of science questions we want to think about. So we really want to characterize the composition of the lake itself at different depths, as well as the seafloor and then the inlets, like near where the rivers are. We also want to look at this photochemically produced aerosol distribution. So remember, the aerosols are being produced in the atmosphere, but we expect that they're drifting down to the surface. They may be in the hydrocarbon bodies, they may be along the shorelines at the bottom. We don't know. There's a lot we still have to understand. So we really want to study these distributions as well. We want to use stable isotope ratios to study Titan's atmospheric history and understand what's going on with the atmosphere. There's a lot of questions and mysteries still that we really want to understand, and also to look for biosignatures. So as we've identified habitability as a really key question, we really want to see if possibly there could be really strange life existing in the lakes of Titan. We want to look at the seafloor to understand the missing ethane. So while this might seem like a minor question, it's really kind of interesting because the photochemistry of Titan's atmosphere suggests that there should be a lot more ethane than we actually see. So by looking for this missing ethane, we can understand whether we're really modeling the atmosphere wrong, or if the ethane is kind of sequestered somewhere on the seafloor and out of sight from Cassini. And finally, we want to remain in Titan's system for 5 Earth years, which would allow us to really understand seasonal and weather variation and see how the hydrological lake system in these lakes are modulated through different seasons and weather patterns. And then our second goal is, of course, sample return. So we, for the first time ever, want to bring back samples from an outer solar system satellite to Earth. And we want to do this in a threefold manner. We want to get a liquid, a solid, and an atmosphere sample. We want to take one each of solid and atmosphere, and then 4 different liquid depths, and return them to Earth for scientific analysis in our labs, where we can conduct much more thorough and rigorous science than we can in situ. We want to take each of these samples in triplicate for rigorous scientific analysis.
All right. So we want to get there, but how do we get there? Well, it turns out it's really, really hard. And we, straight out of the gate, began hitting all kinds of walls that are just fundamental physical challenges set by nature. It's not easy to get this far out of our solar system. Much more, it's especially hard when you want to dip into a huge gravity well that's full of soupy gas that's trying to prevent you and keep you staying there. The second question is, this soupy gas is moving fast. There's very high winds in the upper atmosphere, and it's very hard to get a certain landing spot. And so that requires a lot of potentially undeveloped or unassessed new interventions, or an alternate modality altogether, reconsidering sort of how we're going about this process. The second one, there are honestly way more than I could even list. I'm doing an injustice to all the other problems that we had to face. But one huge one is Titan's really cold, and these samples need to be preserved. We don't want to break down very interesting, for instance, solid properties. So you can have clathrates, you can have co-crystals. If you're melting these, you're losing the interesting structures. And some of these have phase trapping. So what happens is, if they've experienced high pressures in their history, they'll have interesting properties, and that can tell us if they're cryovolcanoes, for instance. If we heat it up too much, even by 2, 3, 4 degrees, where this stuff melts, and we lose all of our information. So we need to be very careful about the thermal side. And so, looking at all these options, we mapped out a whole range of possible architectures, different modalities, different combinations of either existing proven technologies and different new approaches. If you look briefly here, you can see that these sort of break down into using Dragonfly heritage and trying to leverage the advantages of a rotorcraft, having been proven in the Dragonfly missions. And then a second interesting premise, which is the first space boat. So effectively what this means is landing on Ligeia Mare itself. And this actually works out great because Ligeia Mare is actually quite huge, and we can fit our landing aeroelipse very much inside of that region and count on landing without having to do any exceedingly complex interventions. With some other clever technology solutions, we can globally beat all of our other design considerations, or all of our other candidate designs, and we move forward with the boat and submarine, and which we'll be telling you a little more about shortly. So how do we get a boat and submarine to Titan? This is just a brief overview. These acronyms will be showing up a little more in this process, but the basic idea is you go interplanetary to get to Titan in the first place. You leave an orbiter leave an orbiter around Titan. you entry, descent, and landing this boat, we're calling it the Buoyant Titan In Situ Explorer, into the lake, which then can deploy a probe to collect samples both from the liquid of the lake and the floor. And then you send up your ascent vehicle, which can meet up with that orbiter, deposit its capsule, and that can be sent home. This system, you'll note, if we go into the overall architecture and how this works, we got the sampling on the surface, atmospheric, liquid, solid, and we have coming in from Earth. This is where we split off EDL. The combined return vehicle and orbiter remain in orbit waiting for the sample rendezvous after we go through this collection process, after which we have this return home, and we keep the orbiter and bodhi on Titan. And that means that they can continue doing science, putting around this fascinating lake.
Yeah. Yes. So as you're probably aware now, we have a multi-vehicle architecture to solve this problem. And at first glances, it seems fairly complex. So I just want to very clearly define what each of these vehicles is doing in the overall operation. So that's very clear from the start. So first we have the ITV. This is our interplanetary transfer vehicle. This is really the workhorse of the system, and the rest of the vehicles are stacked on top of this in the launch vehicle. And this, the ITV is responsible for the transfer both to the deployment of all the other vehicles and then the return of the sample to Earth. So it will also conduct the rendezvous with the sample container once it's descended from the Titan surface. Now we also have the TOE. This is the Titan orbital element. This is the spacecraft stacked directly on top of our workhorse ITV. Now this system will be left in orbit around Titan once the sample collection mission has been completed. So we have a 5-year science mission in a 1350 kilometer altitude polar Titan orbit. And this vehicle has a suite of instruments which will supplement the data measured and the science conducted by the bodhi instrument on the ground. And then the final primary vehicle in our stack that you can see here is the Titan entry vehicle. And this system is responsible for conducting the entry, descent, and landing onto the Titan lake surface, and it carries our bodhi system down to the GMRO. So, in terms of operations for our sample return mission, we have a Titan arrival date of around 2045. This corresponds to a launch date of 2036. Upon arrival in Titan orbit, the Titan entry vehicle is deployed from our primary stack, and it conducts entry, descent, and landing. We have a 60-day sample collection mission in which bodhi will collect the 3 samples, as you can see here at the bottom of the operational diagram. The Titan ascent vehicle will then conduct the launch from the Titan surface and release our orbital sample container into Titan orbit, at which point the interplanetary transfer vehicle will conduct a rendezvous and capture of this sample. Now, before leaving the Titan system, we deploy our orbital element so that it can continue its science mission, so we can really maximize having gone to Titan in the first place and leave something useful behind there. With this deployed, our ITV begins its transfer back to Earth with the sample container within it. Yes, so the Titan orbital element sized for a 5-year science mission. Whilst in this polar orbit, it has its own instrument suite to conduct both radar mapping of the surface, and it has a visible and infrared mass spectrometer as well. The instruments will be described a bit more later on. It can provide data relay services for the bodhi instrument on the ground via the Deep Space Network. And we've been very careful about planetary protection here. So at the end of the 5-year mission, we've sized the propellant mass of this vehicle so that the Titan orbital element can conduct a propulsive maneuver to leave the Titan system and go into a stable orbit around Saturn, so there's no risk of crashing back into the Titan surface.
So to enable the 2 primary science goals of both characterizing and understanding the deep structure of the lake and enabling our sample return, we have an extensive suite of instruments selected for this mission. Now, just to remind everyone, we are aiming for the GMR. It's at the north of Titan. It's an incredibly cold environment. There's a lot of great potential science there, and we're not the only ones who have thought about it. We're actually able to use a lot of this previous experience in designing missions like Titan Mario Explorer, the Titan Submarine, the Titan Salmon System mission to better understand what science goals that we should have, and also take advantage of the scientific and instrument developments that they started or projected. So we are trying to look at 4 different types of measurement to support our scientific objectives. First and foremost would be the space-based element that's enabled by the Titan orbit element. That's going to be primarily looking at radar mapping and visual infrared mapping images, similar in vein to Cassini, to help provide a full global coverage and a map of the Titan's surface. Then we'll be looking at atmospheric analysis, primarily focusing on mass spectrometry, but also making measurements of meteorology and the first of its kind video imager, utilizing commercial off-the-shelf technology adapted for the Titan liquid lake environment. Additionally, enabled by the sample acquisition summary, we will be doing a series of chemical analysis focusing on mass spectrometry and a novel technique of attenuated total reflectance spectroscopy, a first of its kind for this mission, which will allow us to actually gather a fingerprint or thumbnail of the sample before we reach over to the Earth, so we can test our sample validity and make sure nothing has changed during transit. Essentially asking, does it look the same when we sampled it in situ? And does it look the same as when we crack open that sample tube back at all? Finally, we want to understand the character of the lake, so we'd like to explore more of the ground underneath Lake Geomari, primarily through uses of instruments like physical properties package attached to both the bodhi and SAS element and sonar measurement. Also included with these packages is a microscopy element, which allows us to take high magnification images of the liquid and ground samples. These instruments are distributed across the three major elements, both in orbit and on the surface. We can see them outlined here, and we see that we have complete coverage of all of our science goals. Now, the great thing about a lot of these instruments is that we are able to select 12 instruments with flight heritage and only develop 3 new science tools from commercial off-the-shelf products already available in laboratories. You can get the sonar from a fishery, for example, and develop those for the Titan liquid lake environment. This gives us, when we look at both the bodhi and SAS package, a low mass but a high surface science return, and allowing us to study chemistry, composition, and structure for a long period of time after the samples have returned back home. So let's talk about the major phases of scientific data gathering. We have 4 phases before the actual sample acquisition, where we contextualize the samples. On our mission out to Saturn, we check out our older instruments like the VIMS and take opportunities or take images of targets of opportunity. When we get to the Titan system, we begin our mapping process to best understand the surface characteristics. And then during Titan descent, we pop open a little hatch and take some measurements of the metrology as we head on down to the surface, allowing us to see a full atmospheric profile above Lake Geomari. Finally, we do very quick sample analysis and characterization, primarily focusing on the microscopy, the sonar element, and the ATR, to make sure that when we send samples back home, we know that they haven't changed too much in transit. However, the most important part about all of this is that after the sample return, we keep on doing science. We are always producing science from the day that we launch, and we continue to do so for 5 years afterwards. First, we focus on studying Lake Geomari, trying to completely map it out, move around the entirety of the lake, use the SAS over and over again with our GCMS and ATR package and microscopy to best understand what the composition and structure is, get a full idea of what this unusual lake looks like. Then, if we get done with that, there are some unique opportunities to move beyond Lake Geomari. There's a few fluvial channels or channels that could go up. There's Mari nearby, which might be connected, but our up-to-date instruments from the Titan orbiter element will actually allow us to maybe explore these places. And then finally, let's not forget that this is a sample return mission. We are bringing a small suite of instruments with us to Titan, but the opportunities for scientists here on Earth are wide. So with those samples finally returned home, we have instrumentation on the surface that will allow us to compare the samples, check for validity, and enable all sorts of advances and studies of astrobiology, chemical composition outside of Earth. So don't forget, not only do we do sample return, but we keep on producing science for the entirety of this mission.
So we'll quickly talk about mission analysis, how all of this happens as a time sequence. So there are 3 main components to the analysis that's been done on the transfer and the orbit. So we first consider the interplanetary transfer, both on the way there and on the way back. We also need to consider how we capture in the Saturn system and eventually arrive to Titan and Titan's orbit. And finally, we need to select the Titan orbit for the orbiter elements to be able to conduct its science. So for the outbound interplanetary transfer, we've considered a couple of sequences of flybys and so on. It turns out that Earth, Jupiter, Saturn sequence works pretty well for us. So with an SLS launching in summer 2044, we managed to fit in our schedule a pretty nice trajectory that gets us to the Saturn system. So it's like this, takes about 8 years, have 2 DSMs, 1 flyby, and arrive to Saturn in 2024, July. So from here, we still need to capture to the Titan system. So that I'll go on in a second, but let's first maybe go through the inbound window in the interplanetary leg. So this is going from the Saturn system back to Earth. Now this time around, Jupiter didn't seem to be so advantageous, so we just have a direct transfer leaving the Saturn system in late 2045. So this is the transfer that gets us back to Earth about 8 years, and we arrive on Christmas Day in 2053. So the Saturn system capture, I'll just talk about the capture, but the exit is a similar process. We come in with a hyperbolic approach to the Saturn system. So obviously, we have a lot of the infinity with respect to Titan as well. So what we do is we have multiple flybys of Titan within the Saturnian system so that we can shave off X delta V. And finally, we have a couple of arrow braking sequence so that we finally arrive to our science orbit around Titan. So around with an altitude of around 1350 to 1500 kilometers, we have a period of about 4.5 to 5 hours. This is an example of ground talk for the photo orbit. This is just for 3 days. So obviously, since we're going to be staying there for 5 years, we get full coverage of the surface. Okay, to achieve the trajectories mentioned in the previous slides, we calculated a delta V budget plan, and these tables lay out for each leg of the trajectory how much delta V we need to be on our trajectory. These delta Vs will be performed by the spacecraft system, by our Oracle, and the top table represents the delta Vs for the transfer from Earth to Saturn and Titan, and the bottom table represents the reverse, coming back to Earth. And as you can see, the top table has a lower total delta V because most of those delta Vs will be performed by the ascent or the upper stage of the launch. Okay, so this is a diagram of the integrated system, of the integrated spacecraft system that will be included in the payload pairing of the launch vehicle. And the total launch mass is about 14 metric tons or 14,000 kilograms. And this was included in our delta V calculations. And
so I'll just provide a brief overview of the interplanetary transfer vehicle architecture. So it's just a high-level description of the sort of systems we can expect on the vehicle. So it's 3-axis stabilized. It requires about 700 watts during maneuvers. And an important design fact to note here is the use of a high number of multi-mission RTGs. Now, we're very aware that the supply of these units can be quite limited sometimes, and the manufacture of so many MMRTGs for a single mission may be problematic. So we have also considered other options. There is the NASA Killer Power project, which is looking to generate a 1 kilowatt fission reactor. Now, this may well be operational or a viable technology by the time this mission launches. But it is important to note still that despite the high number of MMRTGs, both this vehicle and the Titan orbiter still have a lower power requirement than Cassini did. So the Titan orbital element, again, must be 3-axis stabilized to conduct the imaging of the surface. Again, a large number of MMRTGs. And like the interplanetary transfer vehicle, we use a high specific impulse bipropellant system to perform orbital maneuvers. And then we have some other key figures on the graph there. And it's important to note that on all mass estimations of both of these systems, we include a 50% mass margin to account for inaccuracies in these initial estimations.
So the Titan entry, descent, and landing is one of the most dangerous parts of our mission. That's why it's key to use a lot of heritage in our design. As you can see here, this type of landing maneuver is very similar to the Huygens and the Dragonfly mission. But two key differences are that we are actually entering from a circular orbit instead of a hyperbolic orbit, lowering our entry velocity. And second, we're doing a splashdown. It's important to look at the splashdown. We don't want to contaminate water with our propellants. So we've discarded a propulsive descent maneuver and opted for a parachute maneuver down to the lake. This makes one big problem. That's that we still have our back shell and our descent parachute attached to our vehicle. That's why at the end of the mission, once we touch down on the lake, we will separate our back shell using some water. As was said before, one of the big problems that was found during the Huygens descent was that there were high winds in the upper atmosphere. Because we have a long parachute phase, this results in a large uncertainty on our landing location, to be specific, of around 150 kilometers. However, La Gia Mare is luckily a very big body of hydrocarbon. That's why we can fit our landing ellipse snugly into this lake, allowing us to land away from large mass of bodies.
Let's all switch.
Let's switch.
So we've landed on Titan with our parachute, and we now have our vehicle, the buoyant, autonomous Titan In-Situ Explorer, or bodhi. What does bodhi do? Bodhi is an integrated science platform elevated in pontoons. When we were designing bodhi, we had three criteria in mind. We wanted it to be mobile, we wanted it to be extremely stable to withstand winds or waves, and we wanted it to be insulated from the lake. That's why we've elevated our platform on pontoons to limit the surface in contact with the lake. What is on bodhi? Well, first of all, we have our SAS. As a reminder, SAS are the sample acquisition submersible. We have our suite of instruments, avionics, and our Titan ascent vehicle. What are we gonna do on bodhi? Well, we'll have on board a mass spectrometer, and all of the other sample instruments are on the SAS directly. So this is our CONOPS. We've landed with a parachute, soft landing, and then first of all, we can use our orbiter to geolocalize ourselves on the lake. Using our orbiter radar and an onboard sonar, the science team is going to decide where we want to do sample acquisition. And then we'll have a propellers to bring us there. Sample acquisition is made while in station keeping mode, and we have our submersible vehicle that will be lowered underneath bodhi, lowered a tiny bit to do the atmospheric sample, and then lowered at several different depths to do liquid samples. And at the end, we will do our solid acquisition system. Most of the measurements, as I said, will be done directly in the submersible, and on board bodhi will only have the mass spectrometer. Once we've gathered all our samples, we're ready to load them in the transfer in the tab, and the samples go back to Earth. But as we said, we will still have our submersible on Titan that can go back down again, move laterally on the lake to do several sample locations, and use the onboard mass spectrometer to continue to characterize it. This is what bodhi looks like from the outside. The main platform is elevated. It's a cylinder, and it has enough space so that we can deploy the submersible from below for our atmospheric sample. The protruding elements are the RTG for heat dissipation and cameras and antennas. We have 6 pontoons that are pill-shaped, and they will be half submerged in nominal operations. And that will be described later, our propellers all over. A bit more detail, but it will be okay. A lot of the samples, a lot of the systems here will be developed by my other team members later. We have our RTG in the hot section, as well as a suite of avionics, including the communication, onboard computer, guidance, and navigation. Here we have our whole sample handling system. We have 2 SAS for redundancies, and they're mounted on the rotating platform that I will show just after. And we have mechanism to transport the samples either to the transfer ascent vehicle through the OSC or to the mass spectrometer. We have our transfer or Titan ascent vehicle and below it we have stage 0 to lofted before ignition. A bit more of a precision on the sample handling system. This is our SAS. It will be developed just after. And so we are using this rotating platform on which each SAS can also rotate so that we can have access. So each sample can have access to all the instruments we want for the measurements we want to do. It will be lowered, of course, through a winch below the submarine. As I mentioned, a sample has two options. It can either be loaded in the return capsule back to Earth, or it can go to the mass spectrometer, where a mechanism will enable it to be reused, which enable us to continue our science mission for 5 years.
Great. So the bodhi has a couple of deployables, notably the propellers, which will be deployed into the water to get around, the mass cameras to allow it to see, and a sonar boom, which is lowered into the water, both for navigation and for achieving scientific objectives. And for simplicity and reliability, all of these mechanisms are, they use stored energy through springs or gravity, and they're held in stowage by frangible bolts, which means there's no actuators that need to work for these to be deployed. So bodhi is doing a lot on the surface of Ligeia Mare. It has to land, it has to propel itself around the lake, it has to launch the Titan ascent vehicle, and there's some uncertainty about the wind and wave conditions that we might experience on the surface. So we prioritized hydrostatic stability in the design. So we selected radial pontoons because pontoon boat is one of the most stable structures in the water with a short and relatively wide profile. The main body of the spacecraft is elevated only just enough to ensure that it doesn't come into contact with the surface of the lake, which is for thermal isolation. So propulsion is achieved using 6 propellers, which is based 60 degrees around this around the spacecraft. This provides a good deal of redundancy, as each one is capable of being driven both forward and in reverse. And we have 2 main operational modes. The first is moving around from place to place at maximum speed of about ½ meter per second. This requires discharging power from the battery and can only be done in bursts. The second is station keeping. We don't have an anchor, and there are small currents in Ligeia Mare, so we'll need low power from the propellers to counteract the lake currents and maintain our position. And this is something that can be operated continuously with power from the RTG. Speaking of power, our only power source is a single multi-mission RTG. And this enables a continuous full science operations with the station keeping propulsion. So we don't need to hibernate when operating in that mode, as well as some batteries, which are necessary for that full speed propulsion that I mentioned earlier. Now, bodhi is thermally insulated from the lake surface by its pontoon structure and additional thermal insulation. This is to avoid transferring heat into the lake. So the lake has a good deal of nitrogen dissolved in it, and any heating of the lake can cause that to start to bubble. It could affect our instruments. If it were a particularly severe bubbling event, it might affect the stability of the platform. So we wanted to minimize the thermal transport to the lake. The internals are divided into 2 sections. There's the hot section for the electronics, which need to operate at that temperature, about room temperature on Earth, and a cold section for maintaining the integrity of the samples.
Let us present to you the Sample Acquisition Submersible, or SAS. Its goal is to collect atmospheric, liquid, and solid samples from Ligeia Mare and perform in situ measurements in the most reliable and simplest way. So how does it work? The SAS is tethered to bodhi and slowly descends via winch, collecting atmospheric and liquid samples. Once at the bottom, it collects solid samples using a multi-tool for different ground positions and performs in situ measurements. Finally, it ascends to bodhi via winch and delivers the sample container to the ascent vehicle.
So we really have no idea what the surface of Titan's lakes, or under the surface of Titan's lakes looks like, but that's what makes it fun. So in order to acquire specifically a solid sample, we need to understand the hardness of the surface. So the mission for the SAS, particularly in terms of the solid sample, is to be lowered from the bottom of bodhi. This will be done through a tether, which will supply power to the SAS. It will also allow for communication between the SAS and bodhi and for data transfer. So an acoustic sounder can be used to determine if there's any particularly large rocks or surfaces we need to avoid, and also for depth of the SAS. And then additionally, a penetrometer can be used to be lowered onto the surface in order to characterize the hardness. And so depending on this data, we can determine if we need to anchor ourselves onto the bottom of the lake bed in order to acquire a solid sample.
I'm going to tell you about the design for sampling on the SAS. So first of all, we have a carousel of sample tubes that are arranged in a circular pattern. This design has heritage from Curiosity, Mars 2020, and shortly from Dragonfly. So these sample tubes can open from the top and the bottom, depending on what sample we are currently trying to acquire. Firstly, if we do determine that the lake floor is hard, we will need to drill into the lake floor. In order to do this, we need to achieve preload between the SAS and the lake floor, and we will do this using microspine grippers, which latch onto small crevices in the solid surface and have been designed for space missions. Once we have achieved preload with the ground, we use a rotating carriage of robotic tools to achieve the sample. Firstly, we have a coring drill that is designed after the Mars 2020 coring drill. And if the ground is determined to be hard, we will achieve a coring sample. If the ground is determined to be soft, we will use a suction-based sample acquisition mechanism designed based on Draco from Dragonfly. Finally, we will use several instruments to characterize the samples to ensure that the integrity of the sample is not compromised before return to Earth. After doing so, we seal the sample tubes hermetically using a design based on the Mars 2020 mission. Finally, I would like to mention that primarily the tether going back to the bodhi attaches at the top of this assembly on top of thermal fins that are designed to dissipate heat to the ambient cold liquid. However, in the event that there's a failure and the coring drill becomes stuck in the ground, we will need to detach the primary tether in order to retrieve our samples so that we do not lose our science. And we do so using a force-limited attachment at the primary tether and a secondary tether attached to the sample carousel. Here's an animation that shows you the concept of our carriage of robotic tools rotating to the appropriate sample tubes. Finally, a little bit on how we handle the samples after acquiring them. So we initially acquire our samples in a circular pattern along the sample carousel so that all of the robotic tools can reach these tubes at equal radius. However, in order to compactify this array of samples for the return flight without individually manipulating each of the samples, we'll do so using a carousel pattern a carousel design that can collapse itself using a structure called radial pantograph, which has been used before in deployable space structures. And in order to move the compactified bundle of samples from a lower position to a higher position and simultaneously rotate it 90 degrees in order to be able to insert it into the OSC, we'll do so with a single degree of freedom by rotating this lever about a 45-degree angle, which performs both motions at once before a linear actuator finally translates the assembly into the OSC.
Okay, next we have the TAV, or the Titan Ascent Vehicle. This is a rocket designed for taking the samples from the surface of Titan up to our Titan orbital element in space. The trajectory for this was based on values found in the literature, and the mass properties are based on an analogously sized Mars ascent vehicle from a Mars sample return mission. Critically, the vehicle is lofted into the air by a pneumatic arm before igniting and beginning its ascent. This is to prevent the plume from impinging on our precious bodhi and damaging it.
All right, here is a quick view of our OSC, which is the orbit sampling container.
The design has been inspired by the Mars sample canister, and the hexagonal shape that you see here with the holes in the center, that's where the carousel slides into and sits. And so that's how it works. And this canister gets loaded onto the tap for takeoff.
For a brief but key period between launching off the surface of Titan and being and rendezvous in orbit with the interplanetary return vehicle, the orbiting sample canister has to maintain the sample temperature at the surface temperature of Titan on its own without any input from other systems. And the way we achieve this with a simple, reliable, and low mass system is using a evaporative cooling system in which heat that is absorbed into the OS evaporates liquid nitrogen, and the gaseous nitrogen resulting is then vented away into either Titan's atmosphere and space. And this provides that key thermal control for the less than 1 day link between Titan's surface and Titan orbit.
All right, so the tap takes off and sets the OSC or the tow, sets the OSC in an orbit that is 1 kilometer ahead of the tow. And the tow, with its spacecraft capture mechanism, grabs onto the OSC, conducting proximity operations. And it uses a funnel system, and the OSC slides down. And then we jettison the spacecraft mechanism or separation mechanism, and then close the heat shield and set it off on an entry return trajectory to Earth.
Okay, so how much does this all cost? The final estimate is $4 billion, which excludes launch costs, but includes all development, programmatic, and operational costs, both recurring and non-recurring. The cost estimation methodology was based on a top-down analogy-based approach where we looked at comparable missions. And as you can see, our estimates were quite in line with what they had forecasted. It's important to note that because of our strategic mass optimization and because leveraging existing technology, we're ultimately able to drive a lot of cost optimizations from the original estimates between $5 to $10 billion to $4 billion, which includes all mission costs from the start statement.
Okay, and last but not least, we know this is an extremely valuable mission, not only for scientists, but also for engineers. But what the world doesn't know is that this will be a mission that everyone will want to take part of. So we've designed a public outreach program, which basically is based in both education and public support. Education, because we know we need more people in science if we want to keep making these amazing developments. And public support, because we need people to want to do what we do. So our favorite one is the SAS, naming the SAS contest, and we will for sure engage a lot of people of all sorts of ages in this program. And of course, we want to keep everyone informed on what's going on. So we will have media presence, visual imaging campaign, countdowns on TV, or even iterative immersive experiences to show how life on Titan would actually look like. So, well, this is our amazing team, and we all want to thank you for listening today to us, and we will listen to your questions.
Let's just look at the microphone. Thank you very much, Team Explorer, for this amazing presentation. We will now start a 20-minute question period where our jury can ask any questions that they would want to have you clarify. So start the timer now. You just repeat the question for you.
Okay.
Yes, thanks for the excellent presentation and the comprehensiveness of the mission in 1 week. It's impressive amount of work. I wanted to, so science, of course, the motivator for Titan, covered some of the big picture questions, but I want to get a little bit more granular in terms of how did you select your science objectives and also balance the resources that you spent in your mission, your engineering resources, your schedule, your budget, in the charge to return samples, with some degree of analysis versus this additional objective of characterizing Titan in situ. Can you talk a little bit about how you devised your requirements and balanced what can sometimes be two competing goals?
So the question is basically, how do we like balance our like big science questions and the requirements of the mission and the engineering and all these different components? Like, how do we balance them and actually decide what we want to explore in our mission? Is that a good rephrasing?
Yeah, and also maybe when the rubber meets the road and you start going over whatever budget NASA gives you.
Yeah, in the budget. Yeah, it's a great question. I guess like so I was the only scientist and I adopted another scientist along the way. Yeah, so it was kind of like, I think like with Titan, it's such like an interesting place because there's so many questions. Like we haven't been there enough. We haven't really been to these polar regions. Like the questions we ask are really like, there's so many, like it's hard to even know where to start. So I guess like for me, I thought like we should think about what makes Titan distinct. And like really in the solar system, it is these hydrocarbon liquid bodies on the surface. And so this idea that we already had this mandate to do sample return from them. Well, first, they sample return from Titan. Like we've never done like such a long interplanetary transfer. Like the samples could get messed up along the way. So like the immediate thought was we should be doing more science than just that. If we're going to spend resources to get to Titan, we should be doing additional characterization. Then the next step was, well, where are we? The lakes. And since the lakes are such an interesting geological, hydrological, and photochemical site, kind of, I think like the interchange of those three cycles really sparked our imagination and made us start thinking like, where can we really dig in deeper to understand these three cycles? This is really, I think, what makes Titan such a special and amazing place is that there's these different surface processes interacting with each other. And as for the budget and the actual, I have never worked so closely with engineers. I learned a lot. I don't know, we all like each other still, so that's good. Yeah, I thought it was really interesting, like what's actually realistic and what isn't. And so I think that was a lot of like learning the practical side of engineering, because I think scientists want to dream that anything is possible. And it is, I guess, well, to some degree, not really, but I guess, yeah, so learning within the context of the engineering budget was really an iterative and communicative process between us and the engineers.
I'm wondering what drove you on the course. And one thing that we see a lot of HPL is minimize the number of elements, complexity, and overall keeps the mission as simple as possible. So I'm wondering what the decision-making process was to include the Titan orbiting elements, as opposed to just including some of those capabilities on the transfer vehicle itself, and what the big advantages were of dropping off some of that mass and what the actual savings were, as opposed to the cost including an additional element.
Repeat the question.
Sure. So it seems to me that the question is, why keep an orbiter in orbit when you're sending the sample home? And so a big part of that was actually operational. So we needed to know going in what we had in store. And so first of all, we basically need baselines, those baseline instruments. And actually, by leveraging Cassini, we were able to combine effectively the same operational premise. So using the same communications for radar. And then we also have the visual imaging system. And the key thing here is we don't want there to be like a polar storm, right? We don't want to be going in and suddenly find that there's some kind of atmospheric anomaly that's way beyond any of our models, and we end up, not even near the lake, right? And so that was the first thing. And we knew having that, there was already a huge science bonus to having that in orbit, because we only have effectively a 50% coverage currently in our model of Titan. And being able to grow that would be super, super essential to keep building any global geophysical models. And then on top of that, it's basically we need to leave that behind, or it's generally good to leave that behind for delta V and mass reasons, because otherwise we're just lugging it all the way home. And so what it worked out to is it's going to be in orbit anyway. Why not make use of it? And so that's really what came down to. But there was definitely a lot of back and forth between like the operations we needed to do, making sure we had our bases covered, and then realizing there was a lot of science we could make out of what was otherwise going to need to be just additional instruments, effectively. Yeah, sure.
So I just want to say as well, on top of what Lucas talked about, is obviously the primary mission here is that sample return. And we had this fear that, okay, we could have included all of our instruments on the ITV, the transfer vehicle itself. But to get any real value from that, we'd have to have stayed in the Titan system for a period of time. And we had this fear that having performed the sample capture in orbit, all of these sort of critical systems, in order to complete that sample return mission, we have to wait around for, I don't know, 4 or 5 years before even beginning the transfer at home. It's a long time to rely on the system to keep, to not undergo some sort of failure. So with that in mind, we have the idea of getting home as soon as possible, but then that doesn't mean you've gone to Titan for a very short period of time. So that sort of led to the orbital element idea, whereas we leave something behind, but we're not just going to Titan for 60 days, which is a long way there for such a short period of time. But yeah, just want to add.
I'll take it. I'm going to write a little bit on that, all on that topic a little bit more in terms of complexity. This is amazing. I was wondering, and I was happy to see some redundancies in architectural design. How did you decide where it was important to put them?
So when it came to some of the payload and instrumentation, I'll repeat the question. So you were curious about places and how did we make decisions about putting in redundancy in the system design? From the payload engineering perspective, there's a lot of great advancements when it comes to small detectors and imagers, things like that that are lightweight, commercial off the shelves, sensors you can just place on the outside of the surface, like an ultrasonic wind sensor, for example. So with some of the really high value instruments like the planetary, the physicals properties package, it seemed like a natural fit to throw an extra set on there on both the submersible and also on the liquid lander. It gave you the ability for calibration at a very small weight cost and a very small power cost. And additionally, because of the rise of more and more COTS imagers on the market, you'll notice that we actually have 2 variants of the kind of similar camera for the imaging system. Same thing that we actually have on the SAS as well. Things are getting more light. So when it came to science, how could we increase redundancy for the lowest amount of impact? And could we differentiate them a little bit? So for example, we use the lower megapixel imager to do video, because there are these really cool transient things that might happen in Titan's lakes, such as nitrogen bubbles or these magic islands. So why not have something different that produces a little bit lower resolution video, but more of it, and have that kind of functionality interchangeable throughout the payload system? So that's from the payload perspective. There might be others.
I'll also add a bit of the reasoning behind having 2 SASs. So first of all, I'll say that on a mission of this budget scale, it's always a good idea to have single fault tolerance where you can have it. And there are kind of areas of the SAS where it's difficult to do that with a single assembly. For example, while we have spec'd the tether to make sure that it's very unlikely that it fails, it's difficult to include 2 tethers on a single SAS due to risk of tangling. So therefore, in some of these areas, the only natural way to do it was to duplicate the system. And we kind of modeled wherever we could, we drew from heritage and analogs to other missions. And for example, on the Dragonfly system, they have duplicates of the Draco system because it's such a mission critical component. And we wanted to make sure that we do get the sample vector.
Oh, I mean, that's pretty much covered. I mean, generally, there are many different stages of the process where we came to a decision point, we were trying to hash out a design, and then we realized ways that could go wrong. And we were like, we don't want to go through all this effort just for it to go wrong at this point. And oftentimes, it's not hard to make that single fold have another path and another way of getting around it. And so, it could be as simple as adding an extra portion of that tether or having something that break away, like in the example of the collection system, where it's like the top goal of your mission, right? It just doesn't make sense. Or at least we wouldn't feel happy.
I'd like to say once again, thanks for this presentation. It's amazing. I would love to be there to see all the cool. So I have some questions on probability of success, but I think you've answered those very well. I'll go back to the ideation process in the beginning. As your requirements, I noticed that you showed a trade space or and you had some weightings there. How did you actually decompose the overall objectives into those weightings? What process?
Yeah, so the trade space that you saw in the beginning, that's, oh, yes. Yeah, so the question was, how did you go about the ideation process and coming up with the ideas for the architecture of the mission and the specifically the trade space matrix that we had at the beginning of the slides. So that matrix is a science value matrix, and it's based on the JPL 18 philosophy of identifying different architectures to use for missions at the early brainstorming stage. And so the way that works is we identified at a very high level different mission architectures we could use, and we compared them with our science objectives, and we gave each architecture a rating based on how well it was able to achieve the associated science objective. And we also ranked, we also weighted each science objective based on how much science value they provided to our overall goals. And with that, we came up with the optimal mission architecture, and that's what we wanted.
I'd like to follow that question and this question too, but from the science perspective. So I love the ambition of this mission, and Tess knows that I love Titan. And I would love to get, I'm an isotope geochemist, so I would love to get samples of all the things that you're collecting. But what I want to know about is specifically with regard to the STM, right? So you've got what we affectionately call a Christmas tree mission, right? With all of these wonderful instruments, and I love the redundancy of them and the contextualization, like it's fantastic. But you've got a whole bunch of objectives that have multiple investigations and have multiple measurements. And I get that some of the measurements obviously can inform the different investigations and objectives. But what's your, so here's a success criteria question. How many of those things can fail before the mission fails? Where do you define mission success? And what happens if you can't address all of these wonderful questions? I'm not even going to ask about the sample not making it, right? I'm going to assume the sample makes it back and it doesn't do a Genesis, and it's all good. I worked on Genesis sample. I know what they're like. But how do you define that success criteria, given that you're laying out a massive list of things that you're saying we will do this, pick our mission? I mean, even Perseverance, MSL, right? They have very, very specific focus on COSI, I guess. And Tess, you guys have laid out like we're going to answer all the questions, which I love, but at some point, probably not going to happen.
Yeah, you're right. Yeah, I guess. Oh, sorry. So the question is basically when you have a very ambitious Christmas tree mission, which is a great term. Basically, when you have all these different promises and like instruments and things, like at what point is your mission able to be defined as a success? Because the way science goes, it's not likely that you're going to accomplish everything. Yeah, which is really an interesting question. I guess like when I was doing the science research, I was so excited about all these different things we could like see in the lakes. Like there's just such a cool part of Titan, and I was just like we can do all the science there. I didn't really, perhaps focus so much on the fact that like it's a very dynamic system, and we have a spacecraft that's like many AU away, and we're not actually going to be able to do all this. Like something's not going to work out. So I guess, yeah, in that sense, like I think we could consider it a success if we managed like one or two even of those objectives, because like they're all very like broad, like high level objectives. Like if we're like understand where the methane came from, like that is a success. Like that is a very big thing to discover. So like, yeah. I mean, like some of them, like we're like, oh, for biosignatures, like yeah, if we found that, we would revolutionize the world. So like we're not expecting to find all these things, but it was more just like this is all the science that we can potentially investigate, but in no way was I expecting to answer every single question in the STM.
Okay, thank you.
So this is a compliment to that question, but first of all, I'm amazed in what way you put this together. Absolutely. Having been an mission scientist, the hardest thing for me was D-scope, the dreaded word of D-scope, which happens actually fairly early in the mission. And you almost have to say which arm you want to cut off, which flank. So from your team's perspective, if you have to de-scope the mission, because you're starting to run into say cost problems, which part of the mission would you cut?
So the question is, if I have to de-scope, what part of the mission would go? I know my team knows my answer because I've been talking about it all week. I would probably de-scope the sample return. I think there's so much science. that you can do. I have to be honest that if there's one thing that would go, it'd be for me the sample. Damage control.
We could also use like a camera and something.
Which is interesting. I mean, it seems like one of the interesting parts of this mission is its extreme duration of time and its extreme cold. And so, how do you think about that in engineering? I'd love to hear about problems that you encountered. How do you make sure that you have propellants after 6 years or 10 years or whatever? How do you make sure that pneumatic things can still work, you know, next year? Love to hear how you thought about some of those cold time problems. Okay, you want to go?
Yeah. So the question is essentially with a mission of this such a long duration and with such extreme cold temperatures for so much of it, how did we think about operating in these temperatures and operating for such a long time? So the first step in answering that question was that we surveyed the capabilities that we have now for cold temperature operation and the capabilities that are being developed and are likely to be ready by the time of the launch of the mission. And I'd say the thermal constraints on the mission are not, it's not a one-way street where the environment dictates the needs of the spacecraft. The spacecraft can also affect its environment. So we also needed to consider, particularly with thermals, the way that excess heat, either radiating, conducting, or convecting off the spacecraft would affect the measurements that we took. It would affect the properties of the samples that we had. So I think it was an iterative process to get an initial understanding of our limitations, develop some preliminary solutions, determine how those can go wrong, and then iterate on them by either altering or reducing functionality until we got to something that we're confident would work.
I have some specific examples I could give. Along those lines, Eric and I actually had a lot of fun. We definitely got carried away with a lot of maybe very specific problems, but here's an example. So we were originally considering a rockoon, so a balloon lifting your launch vehicle, lofting it above the thick portion of the atmosphere and helping you get your plumes away from your valuable boat, I guess. But here's the issue. You can't get helium to Titan after 10 years. We looked into a lot of ways to get around this, but it really just doesn't work out, and it ultimately doesn't make sense because you're losing so much of that. And we looked into JWST, all kinds of missions that require super tight cryospec, or at least a lot of helium to maintain that cryospec, liquid helium, whatever you want. And it's just really hard. And this comes in all kinds of systems because a given system, they're going to spec it to the minimum for whatever the requirements are. So if you look at, for instance, the propulsion system for our ascent vehicle, its pressurant is helium. Oh crap, what do we do about that? So now we need to use a heavier noble gas, right? That kind of thing. So we definitely had a lot of these kinds of encounters with we even got into like materials because of the issue of like embrittlement and cold temperature. I mean, it gets very low level very quick, but it was definitely very interesting. And the other one was the sample, preserving the sample. So we looked into a lot of options for that because we basically want to absorb that thermal energy. But if you want a gas, then that gas can leak. It's great if you can get something that goes liquid to gas, but the enthalpy change is greater. But then it's maybe better to go solid to liquid because it's solid and it's not going to boil away, So anyway, there's all kinds of considerations. If you go solid to liquid, you have to use a mixture of like ethene and ethylene. It's weird. Anyway, so yeah, we looked into it.
So we now want to open it up to 5 minutes of questions from the general audience and the jury. I know, Morgan, you still had a question.
I can always bug them very
Okay.
So I was just curious, could you expand a little bit more about the forms that you had on the ground, and whether they were on the ascent vehicle or on the
Yeah, so for the OSC, we plan on using a similar antenna structure, like the bow tie antenna structure, such as the Mars ascent vehicle, which would be operating on ultra UHF, and so we can run it off of primary batteries for that close proximity operation. And whereas on the bodhi, we have an X-band antenna, so we can establish direct communication with Earth. And same with the toe, we would have an X-band antenna.
Just a small follow-up, because I think one of the slides you told that you the K-band deep space network. Yeah. So.
Yeah. Okay.
So the Deep Space Network can receive in both Ka and X now. I believe they're moving over to Ka, you know, this sort of over the next generation. The Ka band is really there. It's on the Titan orbital element, and that was really to increase that data rate for the science instruments which it carries on board. The X band has been used for smaller data, you know, telemetry and such, just to reduce power requirements for that particular system. And we specifically use the X band on the bodhi again for power reasons, and also we can begin to leverage Dragonfly's direct to Earth X-band radar, X-band antenna for that purpose. That's why there's that split between the two frequencies.
Hi, great presentation. I have a question about the stats. If I understood correctly, it has all the instrumentation on board, and it has other several mechanisms that need to work at approximately room temperature. How would you collect samples without heating up the lake around the SAS?
So first of all, I guess I'll push back a little bit against the claim that all of these electronics need to work at room temperature. We're drawing strong heritage from Dragonfly, in which the Draco mechanism is at the cold temperature of Titan, which is approximately the same on the surface and at the bottom of the lake. So we believe that our motors will be able to function. We are aware that running electronics in the first place will generate some heat. We have approximately a 60-day mission from the time that we land on Titan to the time that we deliver our samples back to the OSC. We're collecting about 18 samples, which allows about 3 days per sample. So we're planning a long cool down period in between running any electronic device. And we have basically an infinite cold bath and a large surface area of radiators. So we will be able to cool our electronics and not dissipate heat into the samples.
So first of all, love bodhi. Having gone through the same process, I think this was truly an incredible presentation. I also kind of have a question about the thermals. So an RTG outputs 4 kilowatts of heat, and I know that you guys have 7 on the torque spinner, I believe, and then 1 on the buoy. So I was just wondering what your thermal management for that was. Cryogenic type things to cool with them, or basically how you're planning to keep those really delicate samples that our science team has reminded us over and over again have to be kept in a very narrow temperature band. What the plan is for kind of not just maintaining the electronics, but kind of protecting the samples from the heat from the RTG and anything else there.
You want to take the orbital section?
Sure. Yeah. So yes, we have 7 mm RTGs on the interplanetary transfer vehicle. Yeah, it's an interesting consideration. I mean, the first thing you can obviously do is you move them as far away from the area where you perform the capture of the sample container as possible. So they're right at the back of the vehicle on the outside, with their radiated fins exposed to deep space, just to maximise that radiation away from the vehicle itself. And yeah, then you can look into thermally isolating the systems. That vehicle is long; it's 4 meters. And there's pretty much this 4-meter gap between where the RTGs are and where our sample is contained. In terms of the actual interplanetary cooling mechanism, I think we're leveraging the Landis. People saw that presentation the other day. The Landis strategy, where you keep open the aeroshell and expose the sample itself to deep space for the duration of the mission back. That's also why the platform ended up being 3-axis stabilized, so we can maintain that pointing at all times.
So when it comes to the single MMRTG on bodhi, the thermal management for us similar to the SAS. The bodhi is in a dense, very cold atmosphere, So heat that's carried away through convection is already very effective. And while we didn't illustrate it in our diagrams, we have a lot of space on the top deck of the spacecraft for radiative and convective cooling elements. So just based on some very early calculations that we could see just radiative flux on the order of 100 watts per meter squared. We determined that even insulating the bottom of the spacecraft, we have plenty of space on the top deck for that case.
All right, great. So we're out of time for questions, but feel free to ask them later, maybe at the reception and pick their brains about details of the mission. So now we're going to take a 5-minute break so we can set up everything for Team Voyager, and I'll see you back in 5 minutes.